Hello everyone, I am Amarasingh AU under registration number EG2020-3817. So, in this Big Data Assignment 1 assignment, I will be walking through your real-time time order processing system built with Apache's Kafka. This project demonstrates key big data concepts including message streaming, produce, producer-consumer patterns, error serialization, retry logic, and dead letter queue handling. This system simulates an e-commerce platform where orders are generated, processed, and monitored in real time with automatic error handling and recovery mechanism. So let me show you the architecture. We have three main components. So this is the first component. So in this Docker Compose YAML file, this is Zookeeper, and it is run on port 2181, and it is manages Kafka cluster coordination. So in here you can see the Kafka broker running on port 9092, and this is the message streaming platform. So in this here you can see the schema registry. So here the schema registry is run on port to 8085 and manages our schemas. So all these uh, all these run in Docker containers, and it is making the setup portable and easy to manage. So here you can see the how our Docker containers are running in real time. So this is the Zookeeper one, and this is the Kafka, and this is the schema registry Docker containers. So previously we discussed about the infrastructure layer. So now we will discover into the application layer. So in this diagram you can see the producer generate random product orders at one message per second, and the messages flow through Kafka orders topic, and the consumer process these orders and calculates running statistics. So if there are in failed messages, and they are automatically sent to a dead letter queue for a later analysis. So this for so the overall architecture follows a distributed system best practices with separation of concerns and fault tolerance built in. So now let's go on to the schema and serialization. So this is a critical component in our schema. So let me explain why this matters. So the schema defines three fields: order ID, product, and price. So in using Avro gives us a several advantage. The first one is the schema evolution. We can update the schema without breaking existing consume. So the second one is compact binary format. So messages so messages are smaller than JSON, so it is reducing the network overhead. Also, the third one is the type safety. This schema enforces data types and both producer and consumer. So the last one is the schema registry integration. So it is versioning and compatibility checking are automatic. So the schema registry stores all schema versions and ensures that producers and consumers always use compatible schemas. This is essential in production environment where multiple teams might be publishing and consuming messages. So let's dive into the producer.py file. So in here, uh, does the producer does several things. So in here, value schema and the producer config. So this is the producer back underscore config is the if is to connect to the Kafka on localhost 9092, and it is registering with the schema registry on port 8085. So also it loads the Avro schema from order.avsc. So in the code, you can see the product list. So the producer generate 100 orders with sequential order ID uh, with like order 001, 002, like that, etc. So random products from catalog like laptop, mouse, keyboard, monitor, or headphones. So also the prices are random as well to 10 to 1000. In here, each order is serialized using Avro and published to the order's topic. The delivery report callback confirms successful delivery uh, to Kafka. Messages are sent at 1 per second to simulate realistic order flow. The key here is the producer is completely decoupled from the consumer. It doesn't know or care who processes these orders. So let's dive into consumer.py file. So here is the consumer workflow and the retry logic. So the consumer is where the interesting logic happens, and in the consumer you can see the consumer logic code and consumer.subscribe orders. So from these the consumer subscribes to the orders topic with the consumer group order processor group. It uses manual offset commits, which gives us precise control over message acknowledgement. So here you can see the process order function. So in here, when a message arrives, the process order functions first attempt to process the order and then to demonstrate data handling. So for that, I have added 20% random failure rate. So after that, update running statistics, total price and message count, and then calculates and displays the running average price. So considering about the retry mechanism, so this is the retry mechanism I have added. So this is crucial for production systems. When processing fails, the system tries up to three times. And then waits 2 seconds between retries. If a retry succeeds, the message is committed and we move on. So this handles transient failures like temporary network issue or database timeouts. So considering about the dead letter queue, so in here, uh, if all writes fails, the message isn't be lost. Instead, it's sent to the dead letter queue, or like also known as if or orders DLQ topic. So we attach metadata, the original order, error message, and timestamp. So after sending the message to dead letter queue, so the operation teams can analyze these messages just to later to fix the systematic issues. So here is the manual commit strategy. So notice we only commit the offset after successful processing. This ensures at least one delivery semantics, no messages are lost. Though we might process some twice if the consumer crashes. So let me show you the live demo how the system is running. So so to start the system, we must type in the terminal docker compose up minus d. So the Docker images Docker containers will running. So I'm not going to look up the containers because my Docker containers are already running in here. So you can see the three Docker containers are running. So if we type docker ps command, so we can see the running container. So as you can see, the zookeeper one and the Kafka and the schema registry is running. So now we can start the consumer file by writing Python consumer.py. So now the consumer starts and it is waiting for messages. So in a new terminal, you need to run the producer file. So you must write the terminal code as produce python.producer.file. So after running that, you can see the live output from the producer terminal. So the products are produced. So in the consumer terminal, you can see the producer generating. So in the this one, the producer is generating orders with random products and prices. So after in the consumer side terminal, you can see consumer receiving and processing them. So in the here there are check marks, tick marks, correct tick marks. These are the successful processing. So also there are warnings. So there are warnings coming because of there are something when a retry happens. So there is a warning. So as you can see in here, so there is a red cross mark. So the cross mark it means that the messages are go to the DL queue. So that's how the terminal is uh, running. So also you can see the running average updating in real time. So the running average give us a real-time analysis in a production system. This could be monitoring average order values, detecting anomalies, or triggering business rules. So let's summarize the key takeaways and conclusion. So let me summarize the key concepts. So the first one is distributed messaging. So Kafka produces reliable, scalable message delivery between producers and consumers. And the second one is schema management. The Aurora with schema registry ensures data compatibility and enables evolution. So the third one is tolerance. The retry logic with exponential backoff handle transient failures is failures graceful. So the fourth one is the dead letter queue. So permanently failed messages are preserved for analysis, not to log. The last one is the real-time analysis. Analytics stream processing enables immediate insight from flowing data. So in production control considerations in the real systems, we must add multiple consumer instances for horizontal scaling, monitoring with Prometheus or Grafana. So more sophisticated data handling should be done, and security should be SSL and authentication security parameters. Also, the data persistence and the backup strategies should be there. So the these patterns are used by few companies like LinkedIn, Netflix, Uber. So for real-time data pipelines, event sourcing, and microservices communication. So this is the my project. So thank you for watching. The complete code is available in the repository. So thank you.